Hi Deepali, can you hear me and see my screen
Yes, sir, audible.
uh, and the screen? Can you see the screen?
Yes, sir.
Okay. We'll wait for some more time, let others join, then we'll start at 6, 2 or 3 maybe. All right, anyway, let us start. Let us not wait for others, let them join in their own time. So, as of now, we have been solving circuits. In fact, in this whole course, we'll be solving circuits, except for the last 3 classes where we will be learning about machines and then solve the circuit of those machines. Now, for the last 4 classes, the way of solving the circuits were mostly one very known thing that you have already studied in your +2 level, that is KCL, KVL, and a bit extended version of them, or maybe you can say application of these rules, nothing but just other way of writing. For KCL, it is node, and for KVL, it is mesh. For comparatively more complicated circuits, we use this. As of now, we have not used any kind of so-called circuit theorems, which we will use today. Mostly the circuits that we will solve today will be solved by Thevenin's theorem. We have to so-called Thevenize the circuits. Um, so Thevenin's theorem, or Thevenizing a circuit, means that, say, we have a network. It has dependent and independent sources inside and impedance networks inside. Now, if it has 2 ports, or sorry, 1 port, that is 2 terminals, how the circuit looks from that terminal, and whether we can simplify that in terms of one independent source and one impedance, like this. Sometimes this thing is also uh, depicted as one independent current source in parallel to one impedance. So basically, the first one is called Thevenin's theorem. Second one is called Norton's theorem. It's basically the same thing, like this. Now, last day I told that we will discuss today about um, voltage and current sources. So that is kind of Voltage source is intuitive. If I write in this way, let me remove this here. Now, voltage source, if I write versus current source, if I talk about ideal voltage source, that is like this. Now, what does an ideal voltage source do? Ideal voltage source always maintains a constant voltage across it. Doesn't matter how much load is connected, assuming that it can mm, handle any amount of current, any amount of load current. The load voltage will not change. So whatever the load might be, this voltage will not change. Similarly, for a current source, whatever the load might be, the current that it supplies does not change. So if I call this I, now for a ideal voltage source, when you uh, connect load, V is constant, V times I is power. Now if you keep connecting the loads in ideal voltage source, we connect the loads in parallel like this. So when you keep connecting the loads, what happens? V V stays constant, but I keeps increasing. So with increasing load, current keeps increasing. As a result, power keeps increasing, but the voltage is constant. It is like this. So the more the load in parallel, more you have current, resistance is reducing. Like that you can think. And you have more power. In current source, what happens? All these loads come in series. Now this is a bit counterintuitive. You think it in this fashion. Say, for example, we live in a world of voltage source. The power supply that comes at our house is rated for a certain voltage source, and it has a maximum current capability. That's a different thing. But it is rated for voltage source, such certain voltage value. So whatever apparatus you buy from the market, they are rated for certain voltage. They are not rated for certain current. They require certain current. Similarly, had this been a world of current source, all our apparatus would have been rated for a certain current, right? Say, for example, in that world, maybe India's domestic current supply is 2 ampere. So all the devices come with 2 ampere current, and depending on their power capability, how much power they need, their voltage rating changes. So all the loads are connected in series in a current source, and they all are carrying the same current. Now I is constant, as you can see, same current flows. So more resistance you have in series, more is the voltage, and hence more is the power. It is like this. Okay. Now if we look at switching, how to turn on or turn off a load. Now definitely when you're talking about turning or on or off of a load, you have to make sure that other loads are not affected. That is, you should be able to independently control a load. For voltage source, we know what we do. We simply add switches like this. So when you close a switch, that load operates. When you open the switch, that load does not operate. In case of current source, we have like this. So we cannot connect a switch here. We cannot connect a switch here, because that will affect all the loads. And it has another problem also that we will see later. So what we have to do is we have to short circuit, or we have to put a switch parallel to each load. So in voltage source, the switches were in series with the load. In the current source, we have to put the switches parallel to the loads. If you want to energize a load, you have to turn on means open that switch. In that case, that load will get the current. And if you don't want to energize, you close the switch, it will short circuit the load, it will not get the current. Like this. Okay. And what else? Yeah, that's all about the ideal voltage and current source. Okay, one more thing. Now, say you want to cut off the supply completely, like a main switch of your house. So for a voltage source, you will have a switch here. You will have a switch here. So if you open this switch, no load, not, I mean, any of the loads will get power from the supply. Even if their corresponding switches are closed, they will not get supply. But for a current source, you cannot have a switch like this. You cannot put a switch in series with the current source. Why? Because the definition of current source says that whatever the situation might be, the current is constant, must be constant. Now, if you keep a switch here, if you keep it open, you're basically violating KCL. So you cannot violate KCL, right? But what is the problem will happen? What that will happen, that we will be more able to understand when we look into the real current source. Just hold for a second for that. So for a current source, we cannot do that. To how to turn off a current source, that is by connecting a switch in parallel with the source. Simply close the switch. So you are short circuiting the source, and the whole current will flow through this switch. These loads will not get any current. Okay. Now we will go into look into non-ideal case. Non-ideal voltage source. Non-ideal voltage source, you already know that it is an ideal voltage source in series with a very small resistance like this. This is V, this is R. A non-ideal current source is again an ideal current source which is in parallel with a shunt resistance whose value is very high. Now, as you can see, for an ideal case, this R tends to 0 in case of voltage source, and for an ideal case of a current source, this R tends to infinity. R tends to infinity means open circuit. But a non-ideal current source will always nothing but an ideal current source in parallel with a large shunt resistance. Now you will be able to understand why we cannot open circuit the current source. We will go into that. Let us first look at the voltage source. Say we short circuit a voltage source. What will happen? A current will flow, ISC. So how much is ISC? I short circuit. I short circuit is V by R. Now V as R, as I said, is very, very small. So if R is very small, the current that will flow is very large. Very large. Right? So no voltage source can withstand this current. And if you short circuit this source, what will happen? See, this whole thing is your source. Maybe say a battery, maybe a DC generator. So if you short circuit this large amount of current will flow through this R, and it will cause a very large amount of I squared R loss, heat, and that will damage the supply, whole voltage source. Similarly, if you open circuit a current source, say if you simply leave the current source like this when it is not being used, what will happen? It's an ideal current source. So whatever might happen, this will push I amount of current always. So if it is open circuit, this current will flow through this resistance, and a power loss of I squared R will happen. Now this R is very large, as I said. So the power loss will be very large, and that will damage the current source. So when the voltage source is not in use, you keep it open circuited, right? When the voltage source is not in use, you keep it open circuited, not in use. And when the current source is not in used, you keep it short circuited. Because what happens if you short circuit? If you short circuit, then the whole current I that flows through this path, and the current through resistance is 0. This load resistance is not load resistance, shunt resistance is 0. Okay. And since the current is flowing through a path that has no impedance, then the power loss is 0. Similarly, for a voltage source also, if you keep it open source, there is no current through the voltage source, hence the power is 0. This. Now we will look at loading of non-ideal current source and voltage source. Loading, if we see, this is the voltage V, R, and this is R, the load resistance RL, let us say. Now this is variable. Now what happens when I reduce the value of R? I am reducing the value of resistance, means I am increasing the load because the load current is increasing. So always keep this in mind that in electrical engineering, whenever we say load is increasing, that means load current is increasing. Okay. So if the load current is increasing, then basically we have to reduce the R. Now, since there is a resistance in the source, you can do this by yourself. You will get to see, very easy to find. We have to find the characteristic of the voltage source. Now see, voltage source, when you are drawing a graph, on the x-axis you draw the independent variable, y-axis you draw the dependent variable. For a voltage source, did I say it right? Yes. Independent variable. So what should we do? Where should we write the voltage? Say you are doing an experiment. So by in experiment you are varying R and you are changing I. So I should be on the x-axis, V should be on the y-axis. You are changing I. For a given value of I, you are getting the voltage, load voltage. So what you will see is when there is no current, so when the voltage source is open, you are getting the full voltage. So I call this OC. You are getting the open circuit voltage, which is basically the voltage of the ideal voltage source. Now, if you keep increasing, it drops like this. Keep increasing R. So here, what happens? Here R becomes 0. Here R was infinite, means open. If you keep increasing, R becomes 0. So the current that flows at this condition is the short circuit current. Right? Similarly, if you look at the loading of a non-ideal current source, what happens is the same thing. You have load. So output, so say again, think about the voltage source. We want voltage from the voltage source. Now, non-ideal voltage source. So when we load it, we do not get the enough voltage from the voltage source. Similarly, current source. When the current is non-ideal current source, we do not get enough current from the current source. So like that you can think. Say this is the load resistance RL. And now if you draw, now here we have to write V here and I here, because what we are getting by changing RL is varying load voltage. Right? And then we are seeing for that much of load voltage, how much current is flowing. What you will see is it is again dropping like this. When voltage is 0 means short circuit, it means RL is 0. That time you have the full. So if I call this ISC, you have the full short circuit current. You keep loading, means keep increasing R, current reduces. And finally here what you get is VOC. Okay. And this is corresponding to tends to infinity. Okay. So this is the reason why we say that you can never open circuit a current source and you can never short circuit a voltage source, and this is how they work. Now tell me your doubts. Is it clear, the whole thing? Okay, so as I said that we live in a world of voltage sources. That is why all our protection or protective gears like our MCBs and other relays and all, they are all meant for short circuit protection. Means if there is a short circuit, it will trip. It will trip means it will open circuit the source. Had this been a world of current source, or had we been working with current sources only, we would have protective gears or MCBs maybe, which would um, protect us against open circuit, and it would short circuit the source when the voltage is excessively high, right? Okay, okay, tell me if there is any doubt from what I discussed now or in the last classes, any class, any lecture. Go ahead. Can you hear me? Could someone please confirm that you can
Yes,
hear
sir.
me?
Yes, sir.
Okay. Okay, so if there is no doubt, we will directly start solving the problems as much as we can today. So we have been given a circuit. The question is, for the circuit shown in figure 1, Thevenin's equivalent network across terminal A and B, we have been asked to Thevenize the circuit. But do you see something wrong in this circuit? Do you see something wrong in this circuit?
Hello.
Yeah, go ahead, Dipali.
Current direction are wrong and also already open circuited. A or B.
Sure. Which is open circuit? Go ahead once again, please. So this 5 ampere so current source is open circuited. If we have to have a 5 ampere um, current here, there is no path for the current to flow. So even if you consider that this is an ideal current source, then also this will not work. Why I will tell you. Think about a physical circuit. You have a physical circuit and two wires came out like this, which were connected. Now you snap the wire and make open circuit like this. Then what is the resistance between these 2 points? There is a path for the current to flow through the air. So the resistance is extremely large, tends to infinity. Now this 5 ampere current, if you open circuit, this will flow through this infinite amount of resistance and will cause infinite amount of voltage. What will happen if there is infinite amount of voltage? I'm sorry. Or if the voltage tries to become very high, what is the phenomena called? What will happen is dielectric breakdown. The insulator that you have in between, say in this case air or maybe something else, that will start conducting, and it will cause a huge amount of power loss. The circuit will fail. Okay, any doubt? So it should be none of the above. This the circuit is not correct. Okay, we'll go to the next question if you don't have any doubt. Okay, we have a circuit. They say for a black box shown in figure 2, the black box contains resistors and independent DC sources. Okay, the current I measured by the moving coil ammeter A is 4 ampere and 2 ampere for R equals 0 and 3 ohm respectively. Okay. Before going into the question, can you tell me what is the moving coil ammeter and what is the another type of ammeter? What is a moving coil ammeter? A moving coil ammeter is used to measure DC current. At the end of this course, you will study DC machine. Then you will see that a moving coil ammeter is nothing but a DC motor, which has magnets inside and a coil inside. That's why it's a moving coil. And the load current that you are trying to measure flows through this coil and it gets a torque, but it does not keep on rotating like a DC motor because the coil is stopped by a spring and the coil is also connected to a pointer so that the pointer moves on the dial and you get to see the current or get to measure the current. What is the other type of ammeter to measure AC current? You are doing basic electrical labs in your colleges? I'd like to know. Deepali, Renessa, Rishi.
Yes, sir. Yes.
They are using these ammeters.
Yes, sir.
So these two ammeters you have used, MC and MIA.
MCA.
What is the other one?
Moving iron. Actually,
Yeah. So MIA is used primarily for AC current. Now, since MIA measures the current by the principle of RMS, you can also measure DC current with MIA. But with MC, you can only measure AC current. This is because if you give an AC current to this coil, which is oscillating say at 50 hertz, it will try to rotate the coil, but the coil has some inertia. At the end, the net torque will be 0. In fact, even if the coil is very light, then also the net torque will be 0. But you will not get to find any current value out of it because it will keep oscillating. Okay. Now the question is this MIA, sorry, not MIA, MCA. Although you can connect an MIA here, is DC circuit, is 4 ampere, 2 ampere for 0 and 3. So basically what they mean is this black box, since it is made of independent DC sources and resistors, we can write the black box like this. This can be the equivalent circuit of the black box. That will have some V, say VTH, Thevenin voltage, and RTH, Thevenin resistance, and the load resistance is R. Now the question is, when R is 0, so basically when it is short circuited, so VTH by VTH by RTH is 4 and VTH by RTH plus, and when R is 3 ohm, so RTH plus 3 is 2. These two they have told us. Question is, for R equals 5, what is the value of current? Now can you solve these two circuits and tell me the values of VTH and RTH? If you solve, we will get VTH 12 volt.
So kindly give us some time, please.
Okay, go ahead.
So the RTH will be 3 and the current will be 1.5. Is the answer correct, sir?
Oh, sorry, I was talking and I was on mute. What I say it is, let us go step by step. Mm, you said RTH is 3 ohm, so VTH is 12. From this equation, you can say that.
Yes, and the current is 12 by 8, so it will be 1.5. The current will be 1.5 ampere.
And if you have a 5 ohms, basically, what I am showing in this red loop is the black box. And they have said that we are now connecting 5 ohm resistance. So the new current is 12 by 8, which is 1.5, as you said. Okay, is it clear, the way of solution? Since the question said that the black box consists of voltage source, independent DC sources and resistors, we can write it's a VTH and RTH like this, and the current is there. We could have done it like this also. We could have said that it's I, Norton's current source, IN, let us say, and a resistance RN, and there is a load. This also we could have said. Then we can solve like they said that short circuit current is 4 ampere, so clearly IN is 4 ampere, and RN would anyway come out to be 3 ohm. Then we could solve the circuit. Same thing. Okay. Okay, we'll go to the next question then, if you don't have any doubt. Question is, consider the circuit in figure 3. The maximum power in what dissipated in the variable resistance RL. So it's a maximum power theorem question. We know that if we have a source,
Before you tell the answer.
I'm sorry, I couldn't hear you. Could you please go say once again?
Kindly give us some time before you tell the answer.
Okay. So you want to look at the last question once again, or want to see the new next question?
No, I give us some time for solving the.
Okay.
Yes, sir. That is only. So give us kindly some time.
Okay. 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 So we'll look into this question then. Actually, what happened is last class we solved a lot of circuits by node analysis. I remember you were not there. So node analysis requires a lot of variables and all. So I assume that students can solve, and they didn't object also. If they had said that, "No, we want to solve it right now," I could have given time. So as you said today, you will get time to solve. I will just write the equations. Anyway, so maximum power transfer theorem says there is a source resistance and load RL. So maximum equals the source resistance. That is the thing. Now the question is the maximum power that dissipated in the variable resistance RL. So basically, it is understandable that we have to Thevenize the circuit at this port between these 2 points. How the circuit looks from here, we have to find out. And once we do that, the circuit will become something like this. We will have a Thevenin voltage, we will have a Thevenin resistance, and the RL, and then we will set RL equals RTH and then find out how much power is being dissipated. That will be the answer, maximum power. Now this question has been made complicated by putting not complicated, we have to anyway find out the voltage, but there is a dependent voltage source. So when there is dependent sources, voltage or current sources, you cannot find out um, the resistance by disabling the sources. Why? What we do while finding on the Norton or Thevenin resistance, we replace the voltage sources with short circuit, and we replace the current sources with open circuit. Now, okay, let us keep the problem here. I will go to our discussion once, and this we will say once again. So in Thevenin theorem, we know, or Norton's also, when trying to find out the circuit resistance, what we do is we replace the voltage source by a short
Amperes.
circuit. Sorry.
110 by 7.
Okay, that question you are saying. Okay, we'll go into it. I'll just telling you one more thing. So we replace the voltage source by short circuit, and we replace the current source by open circuit. So what is the reason behind this? Why do we do so? So if you look into
But I did it with node analysis applying afterwards, and then I solved the equations, which is V1 minus V. And in the solved, like I got three equations and I solved them. So
okay, we'll look into it. What I'm saying is, you know this thing, right? How to apply Thevenin, that you have to replace the voltage source with short circuit and current with open circuits. So I was trying to explain the reason behind that. So what we the reason behind that is, so if you have a non-ideal voltage source, if you want to disable That means there is no voltage at all. No voltage means means it's a short circuit like this, but there is the source resistance present. Basically, what we do is we replace the voltage source with its internal resistance. If it is ideal, then it is zero. Similarly, for a current source, we replace the current source with the shunt resistance R. If it is an ideal current source, this R tends to infinity, means open circuit. This is the reason. Okay, now we will move into it. As I said that there are dependent sources here, so we cannot simply disable the sources. So short circuit the voltage source, open circuit the current sources. So what we have to do is we have to find out open circuit voltage at this point and short circuit current at this point, and the Thevenin resistance will be simply open circuit voltage by short circuit current, like this. Now let us draw the circuit once again. It looks like we have to apply node voltage, node analysis. So if you draw the circuit, you can identify the nodes. This is open. Now we have, sorry, we have 4 ohm, 6 ohm, 2 ohm, 12 volt, 45 volt, 3 ohm, and this is Vx. Now what we have is, now we will take this one as 0. So this is 12, and this voltage they have said is Vx. So we know that this node is at a voltage of 12 plus Vx, and this node we do not know, so let us call the node voltage here as Vy. Now if this is Vy, then clearly the node voltage here is Vy plus Vx. Anyway, so now we have two unknowns, Vy and Vx, and we have two nodes also where we can apply node equation. Yeah, node analysis. 12 plus Vx plus Vx. Okay. Let me just quickly write how much current is flowing in this way. It's 12 plus Vx minus Vi minus Vx. So 12 minus Vy by 6. Okay. Okay, we will now write node equation. So in the first node, this node, we will write the equation first. So currents going out is Vy minus 45 by 3 plus Vy minus 12 minus Vx by 4 plus see this 12 minus Vy by 6, the current that I wrote, that is coming in. We were finding out currents coming out, so we have to write minus 12 minus Vy by 6 equals 0. This is one equation, and the other equation will be at this node. So currents coming out, the one we already found out, 12 minus Vy by 6 plus 12 plus Vx minus Vy by 4 plus another one is definitely Vx by 2. Whether it is plus or minus, we are trying to find out uh, current going out. This is in this direction, so the current is going out. Yes, so this equals 0. And so did you solve the circuit by these two equations? If you do this, you should be able to get Vy. Did you get these results, or you want to solve? First, you tell me, did you use these two equations? Or did you short circuit the voltage sources? You cannot short circuit the voltage source here. There is a dependent voltage source. Can you hear me, Renessa? Okay.
Sir,
So
am I audible, sir?
yeah,
It will be V2 minus V1 by 4 plus V2 minus 12 by 2 plus V2 by 6 is equal to 0. And V1 plus V2 is equal to 12.
wait. Your V1, your
Sorry.
V1, V2. Wait. Your V1, V2, my Vy, Vx looks like they do not match. Can you just match your equations with them? I have marked Vy and Vx in the
I am
circuit.
saying V1 plus V2 is equal to
What?
12.
Which one is V1?
Our
Which one is V1? Which one is V1 in your case?
portion is V1 and V1 minus 45 by 3 plus V1 minus V2 by 4 minus V2 by 6 plus IN is equal to 0 and which is and one other is V2 minus V1 by 4 plus V2 minus 12 by 2 plus V2 by 6 is equal to 0. Sorry, then the equation is coming 7V1 minus 5V2 plus 12IN is equal to 180.
So you took one current here because it looks like a super node.
Yes, sir, I took a
Some current.
super note. I
See,
used the
it is
super
not
notes.
required. It is not required in this case because you see, if the load resistance was here, we had to take a current like that. But now we are trying to find out Thevenin's equation, Thevenin's equivalent circuit. So we have removed the load, we have open circuited, and we are looking into the circuit from this direction. So you see now, this current we know. That's why I found out. You see, this current is 12 minus Vy by 6 because we know that this is 12 plus Vx, and since this is Vy, this one, since I took as Vy, I could say that this one is Vy plus Vx. So I know the current at both the nodes of the 6 ohm resistor. So I know the current through the 6 ohm resistor. And since it's open circuited, the same current is flowing through this source. So you need not take a current unknown here. You can simply get 12 minus Vi by X. That will make the things easier. So this one I told in last class also that whenever you are solving circuits, instead of using theorems, first look at the circuit. What will make your job easy? Okay. It
We'll
looks like a
get the
super node.
recording in the YouTube video, right?
Mm-hmm.
We will get the recording in the YouTube in your channel.
Yes, you will get. You will get. So you see
But
what I'm
sir,
saying
my
is
answer is coming, sir,
this answer.
because as you asked to check the node voltages, it's matching also. So I
Okay.
think it's correct.
What is your V1? Tell me. Is it somewhere close to
You mean the
4.7?
values?
Yes. See, I'm not saying that if you do like that, you will get wrong answers. So what I am saying is, um, wait a minute, Vx. So yeah, so what I'm saying is, you will end up doing more calculations and it will take you more time. It will take you more time.
It's 107 by 25, which is 4.29.
Okay. And what is the other one? So you should get
It's coming
Vx.
approximately for 8.
Yes, like this.
It's coming
Now,
7.72.
right. So if it is 7.72, let us say 7.72. Now we have to, our target here is to find out the open circuit voltage. So we have to find out Vy plus Vx. Our target is to find out Vy plus Vx. How much is it? So just add these two equations. No, wait a minute. I took it from somewhere else. It should not be 4. Did you open circuit or short circuit this? Wait a minute. I took this equation. I have a solution. I'm taking data from there. It should come 30 volt Vy. And Vx plus 12 should come as 22 volt. Can you solve the two equations that you have right now on the screen? If you solve them, you will get
We can solve using the Cramer's rule, right? Then you have
whatever
to provide us something.
whatever you think you can solve it first, because such questions come in competitive exams and you have to know in what it will be very first. Anyway, this was the approach in the last class also, that we will mostly focus on writing the equation. We will discuss any doubt about writing the equation, and the assumption is you can solve the equations. Okay, so the open circuit voltage, as I said, is as we saw here, is Vy plus Vx. So the Thevenin voltage is, you can still do it. Thevenin voltage is 30 plus 22 minus 12 from these two equations, which comes out to be 40 volt. Are you solving this? Then I will wait for some time.
Yes, sir, I'm solving it. Kindly wait.
Okay, okay. Keep solving the equation till then. I will just draw the short circuit current circuit.
Sir, my Vy is coming very different. My Vy is coming 28 point.
Sorry, you are mute.
Oh, sorry. What I said is I put
Sir,
these two
my
values.
Vy is coming very different, sir. My Vy is coming
I heard that.
28.8, sir.
What I said is if I put Vy equals 30 and Vx equals 10, these two equations are matching. I checked. So maybe there is some silly mistake in the solution that you did. What I am saying is, let us not concentrate on solving the equations in this class. That is very trivial. Okay. Let us concentrate more on the circuit solving techniques and writing the equations. Then you practice solving or solving faster at home. Okay. And solving the circuits, trying to find out if there is an easier way of solving a circuit. Is it good enough? Or you want to give it another try? And are you doing it once again?
Yes, sir. I'm doing it.
Okay.
Sir, it's not a problem. I'll be solving it later. So you can move on to the next.
No, this problem is not yet over. We have to find out the Thevenin equivalent circuit. Make sure you concentrate on the way of writing the equations. Okay, equations you can solve. That you keep for practice. That you have to solve them very fast in exams and all. But let us think in
So
that
time
fashion.
take this time for the equivalent circuit also. Like just 2-3 minutes, we'll be doing it and then we'll be telling you the answer.
Okay. So equivalent circuit we will find out only when is it equivalent circuit, right? We will find out only when you get the I short circuit. So this I naught we have to find out. This is the short circuit current. We have short circuited that node and now we are trying to find out the current. So what we have is we have VA and VB, and we know that this is VA plus VX. So let us reduce the number of variables. And I naught, three equations. Three unknowns. Let us see if we can write three equations. So let's start from node A. from node A, what we have is we are trying to write, say, the current going out. So VA minus 45 by 3 current going out plus VA minus 12 minus Vx by 4, again current going out. Now these two we have found out. We have to find out this current. This current is basically, if you apply KCL here, then I naught plus this. So I naught plus that current is VA plus Vx minus 12 plus Vx. So VA minus 12 by 6 equals 0. This is one equation for this. And for the other one, if I write, so what we have is 12 plus Vx minus 12. So Vx by 2 plus 12 plus Vx minus VA by 4 plus 12 plus Vx minus VA minus Vx. So 12 minus VA by 6 equals 0. Two equations we have, but we have three unknowns, VA, Vx, and I naught. So we have to find out another equation. Okay, let us apply K node equation on the other node. Let's write the node equation on the other node. There are three nodes anyway. So the other node is I naught current is going out, you can see. So I naught plus, here we have how much current is wait, no, that is anyway done. Okay, so VA plus Vx minus 12 minus Vx. So VA minus 12 by 6, this much current is going out. And we have another current going out, which is no, wait, we cannot apply. Can you find out another equation here?
Sir,
Here
my
should be.
answer came, sir. So my answer came, the RTH will be VTH by IN, which is 40 by 110 by 7, which is 2.54. And power transfer, the power will be VTH square by 4 RTH. The maximum power, it will be 157.17.
Okay, so your answer matches. Can you tell me the three equations? Which equations you wrote? Or
So
what all
my
equations did you
equations I
write?
already said to you. I did using that super node only, sir.
Okay, so you assumed one current here. Here you assumed one current like this.
Yes, sir. And my equations are I already mentioned, sir.
Okay, okay. So if we go ahead like that, but that is actually how many unknowns do you have in that case?
Sir, V1, V2, and Vx. And I know V1, V2, and IN, sorry.
Yeah. So in this case also I
And then
have.
I did RTH is equal to.
Mhm. Okay, one more equation we can write from here by applying KVL on the top loop. like this. So we know the current going in this way, VA minus 12 by 6. I'm sorry, VA minus 12, that is 1 voltage, plus 12 minus, sorry, 12 plus Vx minus VA, that is another. This should be equal to Vx. No, this is giving us 0 equals 0. I'm just trying to find out another equation that we can apply. Oh yes, I got another equation that I can apply. Just look here. See, whenever we are applying this node equation, we take one node as 0. Now we have short circuit. So if this is 0, then this is also 0. So this is nothing but minus Vx. So the other equation is simply Va equals minus Vx. V equals minus Vx, like this. Okay. Now if you solve this, as Renasa said, you will get, she did it first, Va as 4.286 volt and Vb as 7.714 volt. Now from here you can find out the short circuit current, which is 15.71 ampere. Now once you have the short circuit current, you can find out the Thevenin resistance, which is the open circuit voltage by short circuit current, which as we said would come out as 2.55 ohm. And the power you can find out. Now you have two resistances, so the circuit now that you have is like this: V RTH, and you have to equate this also with RTH. So the power will be simply half.
Yes, and it will be ATH squared by 4 RTH. Then it will be coming
Some
it will be
157
coming
you said.
154, 157.17. Yes.
Yeah. So you see, these problems are all about writing the equations and solving them fast if you are appearing for competitive exams and your university exams also. Okay, any doubt? So in supernodes, you have to just keep on finding out what all equations you have. You see, for this case, we had a very easy solution, but I couldn't see it at the very first go. If this is 0, then this whole node is 0. And this is Vx, so this becomes minus Vx. So our another equation becomes Va equals minus Vx. So simply substitute Va equals minus Vx in these two equations. Now you have only two equations, Vx and I naught. You can solve. Okay. Thing is, like this supernode, as you were discussing, I learned about it while preparing for this course only. And as I said before also, like those are star delta star conversion formula and I don't remember. More things you try to remember, maybe it's easier for you to solve, at least in exam, but keep an open mind. Maybe there are many circuits which are easier to solve without using any theorems. Okay, we'll go to the next question if there is no more doubt. I mean, no doubt. For the circuit shown in figure 4, find the value of R in ohm. Where is R there? Such that it absorbs 20 watt of power. It is also known that R is greater than 5 ohm. Okay, looks like we have to solve a quadratic here. That's why they gave this condition, R is greater than 5 anyway. So, all right. Easy circuit. What we can do
So
is,
if we apply KCL at node, it will be V1 minus 2Vx by 3 plus V1 minus 20 by 1. Then the answer will be coming V1 is equal to 60.
okay, let me write. by 3 plus okay, what we are writing is how much current is going out, right? Going out. This is one equation. What is the other equation?
So here can I apply the super node again?
Do you need to apply super node here once again? Let us try to do it with mesh. Okay, I think it will be easier with mesh. Let us not remove this. Say some current I is flowing and I1 goes here. I2, sorry, we should not write I2. We should write I minus I1. So why unnecessarily write more? Um, increment again 3I1 increment plus I increment minus 20 equals 0. One equation. Other equation start from. We'll look into it later. I, then again a drop minus of I minus I1 times 2 minus I minus I1 times R equals 0. Another equation, we need 3. So what is Vx? Vx is 2 times I minus I1. Match the polarity. Polarity is matching, right? 2 times I minus I1. So if Vx is 2 times I minus I1, from equation 1 we can write 4 times I minus I1 plus 3I1 plus I minus 20 or equals 20. Can you solve 1 and 1? Can you solve?
Hello, sir.
Hmm.
Sir, can you kindly just listen to my equations once more, please?
Okay, go ahead.
It will be V1 minus 2Vx by 3 plus V1 minus 20 by 1 is equal to 0. And another will be V1 1 by 3 minus 2Vx by 3 is equal to 20. So then Vx will be coming 0 and V1 will be coming 50.
Tell the second equation slowly.
V1 by 3 minus 2Vx by 3 is equal to 20.
V1 by 3 minus.
Yes, V1 by 3. 2Vx by 3 is equal to 20.
Wait, maybe you are correct. Let me understand this. You are saying V1 by 3. V1 is here. Okay, so V1 minus 2Vx by 3 you are saying. So V1, that is the current, this current I1. That is equals 20 you are saying.
Yes, sir.
This 3 is this 3 ohm resistance, right? Voltage by resistance should be current 20. I think you are taking from the voltage here. Hmm? This 20, you said this is the source voltage 20, Renessa?
Yes, sir. Yes, sir.
Voltage by resistance cannot be voltage, right? Rishi, can you quickly solve this? Oh, there is one R also. We cannot solve. We have to find something. Find the value of R such that it absorbs 20 over watt of power. Forget this. We have to apply Thevenin's theorem. Let us see. We will apply Thevenin's theorem, okay? I think it will be easier. Let us see. I will not draw the circuit once again. Just imagine it like this. We are applying Thevenin's theorem from this point, from this node. So we are trying to find out how it looks from here. Now, what we have to do, we have to find out open circuit voltage, short circuit current. So open circuit voltage means this R I have removed and this is open. So there is no current through this. So while we are trying to find out open circuit voltage, there is no current through this. So there is Vx is 0. So if Vx is 0, then this one is also short circuited. So we can simply say there is a short circuit here. Now, if there is a short circuit here and there is open circuit in this side, a amount of 5 ampere current is flowing. So it is causing a drop of 5 volt here. So the voltage at this point is 15 volt. And since this is open circuit, no current through this 2 ohm resistance, open circuit voltage that we have is 15 volt. Understood?
So using my equation, it came Vx is equal to 0, sir. And V1, it came 15.
You were trying to find out the open circuit or open circuit voltage.
And V Thevenin also came 15 voltage. And I and also 60 by
Wait,
7. Then R
you were solving this circuit or trying to find out the Thevenin's equivalent?
cut the Thevenin's equivalent.
Okay, then it's correct. Then why didn't you tell me when I was trying to solve this? Anyway,
And so the IN will be coming 60 by 7. Then the
okay, let us
RTH will be
do
coming
anyway.
VTH by IN, which
Okay,
is
let us do.
50 by 60 by 7, which will be 7 by 4.
Okay, so I think the open circuit voltage calculation is clear. Now we'll do the short circuit. So we short circuit this, and we have to find out how much current is flowing in this path. So it's a simple case of KCL or maybe node equation, we can simply say I1 is flowing and I naught is flowing. So we have to simplify and find I naught. So what we have is 2Vx minus 3I1, that's a drop, minus, so 1 times I1 minus I naught minus 20 equals 0. That is the KVL in this loop. And the KVL on the other loop is minus 2I naught plus 20 minus 1 times I naught minus I1 equals 0. So we have three equations and we can, three variables, and if we write Vx equals 2 times I naught, that we can write, yes. So this becomes 4 I naught. Now Renessa, tell me what is the short circuit current you got?
60/7.
16/7. Like this?
No. 60/7. 60.
60. So if you solve this, you should get I naught as this. I1 some value you will get that we are not bothered about here. So once we have,
Now we'll be finding the RTH.
yes, so RTH we have
RTH will
is,
be VTH by I naught, which will be 7/4.
so 7/4 ohm we get. Now the
And I
question
don't know,
is,
sir, but there is coming a quadratic equation. Is it possible?
yes, it will be a quadratic equation. See, let me tell you these tricks. What is the meaning of this sentence? It is also known that R is greater than 5 ohm. So definitely they are giving you a condition so that you can come up with only one answer. So the chance is there will be a quadratic equation. And yes,
So
there
my
is a,
equation, then it will be coming 1/7 plus R whole square into R. Then it will be coming 360 square R is equal to 49 square plus 14 R
wait.
plus R.
If you say that first, I can't understand anything from here. So it's V squared. Wait, what did you say?
So it will be 360 square R. 360 square R.
Where is 360 coming from? Wait a minute. Am I doing something wrong here? Open circuit voltage is 15 volt we got.
So it will
And
be
this is
like
7.
1/7 plus R whole square into R.
Wait, I'm completely lost. Just a minute. It's V squared by R, right?
Sir, my answer
Oh,
also came. It will
understood.
be
Yes.
7.33 and
The amount of
0.418.
amount
So
of
as I
current.
said, its R is greater than 5. So the answer will be 7.33.
Okay. So the amount of current that is flowing is this, right? So this much is flowing through the resistance R, and it is causing a power loss of 20 watt. Now this gives you a quadratic equation. So this 4 went up, it becomes 60, so it becomes 3600 by 7 plus 4R squared times there should be a R equals 20. Yeah, now tell me how much R you got. There should be two values
Yes,
of R.
sir. I
One
got the
is
answer. It will be
7.33
R
and
is equal
another
to
one.
7.33 and 0.418. So as it
Hmm.
said greater than 5, so the answer will be 7.33.
Yes. You're preparing for competitive exams? Hmm?
I was, no, actually, it was. I am currently in my first year, so this was in my first semester. Now I am in my second semester, so
Okay, anyway, you can solve quite fast, I see. All right. Rishi, is that clear? Is this problem clear? We'll go to the next question then.
Yes, sir.
Okay. Okay, Renessa asked, you asked one day about this thing, how to redraw the circuits. Maybe in this case, we will have to redraw the circuit. So it says that for the circuit shown in figure 5, determine the value of R such that the maximum power can be delivered to the this. Again, same question, we have to Thevenize. So first what we will do is, we will find out the equivalent resistance between these 2
yes,
points.
before solving, kindly give us some time for solving. Like,
Okay,
just
okay,
give us some
okay, we'll
time so
solve.
that.
Rishi, try to find out the equivalent resistance between the marked points marked with green.
Yes.
Okay, Renee say do not look at the screen, okay? Because we have some time constraint. You match your result with mine. Renee, could you redraw the circuit and find out the equivalent resistance?
Sir, it will be
Hmm.
R equivalent from 4R. It will be parallel. Then, like, we'll be doing a parallel combination. Then it will be 4 by 3R. Then I1 is coming 30 by R. Total I is coming 30 by R. So I1 will be 10 by R and I2 will be 20 by R. So
Wait,
RTH
wait.
will be 5R by 4.
Okay. Yeah, could you redraw the circuit, Vanessa? You were talking about circuit redrawing one day, I remember. Could you
Yes, sir,
redraw
I
the
did it,
circuit
sir.
like this? Okay.
Yes,
Yes,
sir, I
so
did it.
equivalent
And
is
sir,
5R
the
by 4.
yes, sir. And then the I1 will be coming 30 by R. So I1 will be 10 by R and I2 will be 20 by R. And P maximum will be coming 10. So we'll be doing this that VTH squared by 4RTH is equal to 10. And
Okay,
VTH is equal
okay.
to
Wait,
I2R
wait,
minus.
wait. Wait, if you keep on saying like that, I don't understand anything. Let's look at the question. Maximum power can be delivered is 10 watt. Okay. Sorry. So they are saying the maximum power. They did not talk about mm, anything. So you know one thing that when the maximum power is being transferred, the load and the source resistance are the same. So if there is a 10 watt loss in the load resistance, there has to be 10 watt loss in the source resistance also. So there is a total loss of 20 watt. So V squared by R total is 20. So clearly R is 5 ohm. This is the total R. Now, do we know something? So yeah, so 5 watt, 10 watt or 20 watt, 10 watt. So I is how much? Root 2. Is this what you were getting, Vanessa? Oh no, sorry, R is not 5 watt. What I'm saying.
No,
Wait,
sir, I am not getting this. R will be
no, wait. It is wrong. R is 2.5. The total power is 10 watt. So means the power in the load resistance is 10 watt. So the power in source is also 10 watt, right? So total the power loss is 20 watt.
so you. Why don't you put it in that form, sir? VTH squared by 4RTH is equal to 10.
Hmm.
uh, then 100 by 4 into 5R by 4 is equal to 10. Then R will be 2, right?
Yes, I think so. You are applying some formula. Wait, just give me some time.
Sir,
This
if
is
I ask you an off question, will you answer it kindly?
wait a minute. Wait a minute. Why am I getting 2.5? What is the equivalent voltage that you got? Thevenin equivalent.
Sir, it will be VTH is equal to I2R minus I1R, so it will be 10 volt.
Yeah, 10 volt I got. So 10 volt, 5R by 4 and RL in series. Right. Now maximum power they are saying is 10 watt. So load there is 10 watt loss. Now since it is maximum power in the source also there should be 10 watt loss. So 20 watt loss should be there. So 20 watt loss, if this 10 volt is supplying, there should be 2 ampere of current. Why? How much current did you get at the equivalent circuit?
Thirty by R. So I divided it into I
So
one is equal to
basically
10
what
by R
we
and I two is equal to 20 by R.
did is v squared by 4
Yes, yes,
rth.
instead it is equal to 10.
Yes, this will give you r equals 2 ohm. No, but could you understand my logic the way I was trying to do? Something is not correct, or maybe I'm doing calculation mistake somewhere. It's a 10 volt. So at maximum power transfer, both the resistances should be consuming the same power, right? Because they are getting the same current and same resistance. So if this is 10 watt, this should also be 10 watt. So there should be a total of 20 watt. Now V square by R should be 20. So R is definitely 5. So there are two R's in series which are equal. So what I'm getting is 2.5. What I'm getting is R equals 2.5 ohm and the current should be 2 ampere. Oh, I was doing it correct only. I misplaced the things. This R is 2.5 ohm. This is RL. Now this RL is nothing but the equivalent 5R by 4. So R is 2. Load resistance is 2.5 ohm. This is correct. RL. Now this RL that we found out should be equal to 5R by 4 by this theorem. So from there we get Rx 2, this one. Anyway, I was thinking about this one. I was thinking we have been asked to find out this one. Anyway, so yes, RL is 2.5. This is 2. I made a mistake here. Okay, Rishi, is it clear?
Yes, sir.
All right, we'll look into this. My goodness, this is a circuit shown in figure 6. Thevenin is equivalent network across terminals A and B.
Sir, I wanted to ask an question to
Yeah,
you.
yeah,
Would you
yeah.
kindly answer us? Sir, like I was doing one of the mentors classes, like you are taking. So, sir, he was talking about MATLAB, and in your also one of the you also in your one of your reference channel, like I got in your YouTube video, there was MATLAB. So, sir, that person also asked us to do study MATLAB. So, sir, how we need to study and why we need to do this?
MATLAB actually, it's quite a how to say powerful tool compared to these circuits. But actually, what you can do is it's not MATLAB. MATLAB has some toolbox inside that is called Simulink, and you can draw these circuits in Simulink and then solve and then can see whether your calculations are matching with all with the results that you are getting from there. In Simulink, you will get everything like resistance and voltage source and everything. But what I'm saying is it's a quite very powerful tool compared to this solutions. We are only talking about steady state here. Anyway, these circuits will do not have a transient also. Cross check your solutions using that software. But it's actually Simulink, and inside MATLAB there is something called Simulink. You can use that. But the thing is,
And sir,
MATLAB,
what is size then?
what is
Size.
size is quite large. MATLAB new versions, if you download, it's extremely high, extremely heavy, more than 20
No,
GB.
I meant spice, SPICE.
Spice. See, say for example, you know transistors, right? Now transistors and other ICs and all, they have a lot many things, not many non-idealities inside, lot many characteristics inside. Say for example, this kind of inductances, this kind of capacitance. I'm sorry. In the device model, and when you solve the circuits, you get the actual response of the circuit. But I would not suggest you to use at least spice at this level, because you will not be able to appreciate the use of those softwares and it will be a waste of time, what I believe. Simulink is still okay, but spice has a completely different objective. That is definitely not to solve this circuit or this circuit. Its objective is completely different. In fact, in your first or second year, at least I will suggest you not to look into softwares and develop more and more skills to solve the circuits by hand. Why so? This will give you an idea of solving circuit, like how to apply nodes and all, because sometimes you will have complicated networks which you have to simplify. I'm not saying solving, simplify. So it's very important that you get your ideas clarified in these 2 years. Once you start using softwares, no, you stop thinking. That happens with all of us. And MATLAB Simulink, it's a paid software. If your university is giving you a license, that is one thing, or else you have to get a student version. And these are not free software. Spice is free software, LT Spice and all, but I will strongly recommend not to use this software at this stage. Maybe when you will study power electronics at third, fourth year, at that time. Sir?
Okay. Answer, please kindly give us some time for the next answer question to solve.
Okay. I was asking which university are you from, Denison? Can you hear me? We're solving the problem anyway. Thevenin's equivalent network. You keep doing. I will also keep doing. Otherwise, I don't catch up with you. Thevenin's equivalent network across terminals C and D. You would not listen to me what I am saying. So this is easy question because there is no dependent source.
So the
This
answer will
is
be 4, VPH will be 4 and RTH will be 2.
okay. Let us solve this. So this is the circuit to find out the equivalent resistance. So this 1 ohm is short circuited. So what we have is clearly 1 plus 2 parallel to, so 2 ohm, and we have to find out the voltage. So all we have to find out is how much current is flowing here, right? So this is 20 volt, this is 20, and this is 10 volt. So some 10 ampere current flows this way. We don't care about it. We have to find out the current that is flowing in this direction. So let us say a current I is flowing here, of which 6 ampere goes out. So I minus 6 is flowing. So what we have is 20 equals 2I plus I minus 6 times 2. So 2I plus 2I minus 12. So from here what we get, I is 842. Is it 8 and 4 2? Yeah, 2 ampere. So our open circuit voltage comes out to be 4 ohm. I'm sorry, completely gone. 4 volt. So the equivalent circuit that we have is, we have 4 volt and 2 ohm. Rishi, do you understand the open circuit voltage calculation here?
Mm, yes, sir. Sir, but the I value would be
No, wait, I am wrong.
8.
I is 2 ampere, so 4 ampere is going in this fashion.
Sir, I would be 8 ampere, right?
I is 8 in my calculation. Oh yeah, 20 32 4 8, yes. If I is 8, then this is 8 minus 6 2. I don't know how I wrote
2
the correct
ampere,
answer.
yeah.
2, so it's 4 volt.
4. Yes, correct.
Do you appreciate this part, that since there is no current in this resistance because it's open circuit here, whatever voltage we have across this 2 ohm resistance is the open circuit voltage.
Mm, yes, sir.
Okay. Do this, I won't do this. Thevenin's equivalent circuit as seen from terminals 1 and 2. Okay, at least I can find out the equivalent resistance. So short circuit this, and open circuit this. So what do you have? You have 8 in parallel, so 4 ohm and 4 6. So let me draw once again. I have to draw anyway. This 20 short circuit until there. Oh, this 20 short circuit, it looks like 15. These are terminal, and 4 and 2 6 6, another 6, and that is open circuit, so it doesn't come to the calculation. 20 is short circuited, so it's gone. Let me move it. It's gone. So 6 6 3 and 3 15 18. Okay. It's a problem of super node, it looks like, because there is a voltage source without any resistance in series. Let us say a current Ix flows in this direction, and say we have Vx here, and if this is Vx, okay, I will move this. Vx, we know that this is Vx plus 60, and there must be 3 ampere current flowing in this direction. Okay, let us write the equations. Vx minus 32 by 8 plus Vx by 8 going out, going out, going out. One equation. Another equation is coming in, going out. Okay, two unknowns, two equations. Renes, are you solving this?
Yes, sir. I'm solving.
Just let me know whether your answer matches.
Sir, IX will be coming 7.6.
And Vx, are you getting 2 by 3? Is it 7.666?
Sir, I don't know. My answer is coming wrong. I think VX is coming 2.40 and VX is coming 7.66.
Ix is coming 7.66, you said.
Yes, and VX is coming 2.40.
Okay, let me see. 60 plus 2/3. I'm not solving. Okay, I have a solution. From there, I'm taking the values. By 6 minus 5 plus 3. No, looks like Ix will be somewhere around 8. Let me see if they are correct.
Sir, I solved your equations and it's coming IX is confirmed 7.6.
Okay, let me see if the equations are correct. We took Vx here and we assumed Ix is going out. So Vx minus 32 by 8, that is going out, Vx by 8, Ix. And 3 ampere is coming in, so minus 3. This equation is correct. And on the other side, if this is Vx, this is Vx plus 60. So 3 ampere must be flowing this way. So coming in currents are negative, minus 5. Negative, Ix is negative, 3 going out positive. So Vx plus 60 by 6. No, equation seems correct.
So it's the final one is coming 2vx plus 8x equals
No, wait,
56.
wait, wait. I made a mistake. Wait. I assumed this one to be 0. If this is 0, this is not 0. So there is some current flowing here. This
Sir,
is
I
0.
need a suggestion from you, sir. My Thevenin and Norton theorems are not so fluent and clear. So what can I do with that?
Practice, no other way. If the theory is clear to you, those theorems are clear to you. Can you hear me? 6 plus 2. There should be a plus 2. 6 plus 2. No, there is a 5 ampere current also. My goodness, they made this problem even more difficult. Some current I is flowing. This will be the equation. Can you confirm now, Denisa? The mistake was here. I simply wrote Vx plus 60 by 6, but I did not notice this 2 ohm resistance here. So what I did is, I assumed a current of I is flowing in this way. So this voltage will be 2I. So what we can write is Vx plus 60 minus 2I by 6. Now that is correct, but now what we have is we have one more unknown. So for that one more unknown, we need one more equation. So we have I current going out here and 5 ampere going out here. So by KCL, we know that 5 plus I is going down. That is flowing through this 6 ohm. So we can write this third equation by applying KVL. Vx plus 60, this voltage, that is equals to 6 times 5 plus I.
So your first equation is correct, right?
This was correct. See, what I did is I wrote Vx by 8. Okay, so that means I assume this node to be 0. Now, if this node is 0, in the second equation, third term here, I cannot write Vx plus 60 by 6 because this node is not 0 because of this 2 ohm resistance. So I assumed one more current I flowing in this direction. So this voltage is now 2I. So I can now write in the third term of the second equation, Vx plus 60 minus 2I by 6. This corrects the second equation, but we have one more unknown. To do that, we apply KVL in this node, which gives us 5 plus I ampere current going down in the 6 ohm resistance. And we can write a third equation that Vx plus 60 is 6 ohm times 5 plus I. Now we have three equations and three unknowns. First equation is correct, yes. This 2 ohm resistance created the problem. I did not
Then the
make it
answer
equal
is
to.
coming 5.8. It
What
will be
is 5?
5.8, sir.
What is 5.8?
5 IX.
And Vx?
Four point eight. 4.8.
There is still something that is not matching. Anyway, this can be wrong also. So if this is it, we have to find out now the open circuit voltage. Let us say the value that we have got are correct. Okay, let us not think much about it. So with that thing, can you find out the voltage here, open circuit voltage? Just tell me what is the way. You have
We
Vx.
will be applying the formula.
No, you need not solve anything. Just find out 60 plus Vx. That is the open circuit voltage, because there is no current through the 15 ohm resistance. Is it clear that 60 plus Vx will be the open circuit voltage?
It will be 64.8. 64.8.
Okay. You can cross check the values once, maybe solve the equations once, but equations, do you understand or do you find any mistake in the equations? I think the equations are correct now. Equations are correct now, I think. Yes. Anyway, we'll stop today. I will stop recording.
And sir, just